Welcome back. This is video lecture 23.4, and we're going to talk about section 4 in chapter 23, in which we start applying Gauss's law to calculate the electric field created by a distribution of charge. And we're going to focus in this section on a charge distribution that's shaped like a cylinder. So what we're really getting into now for the remaining 3 or so sections of this chapter is the real heart of using Gauss's law, the real reason we teach it. And that's because, or that is, the real reason we teach Gauss's law is that it can be used in certain situations to very quickly and easily calculate the electric field created by a distribution of charge. The trick, however, or the requirement, is that the charge that we're talking about must be distributed in a very symmetric way, with so much symmetry that from that symmetry alone, we can figure out the direction that the electric field would have. If we can do that, then we can choose a Gaussian surface based on that symmetry, as I will show you, and then it will make calculating electric fields very easy. Now, it turns out there are really only 3 charge distributions that have enough symmetry for us to do this little trick. And those 3 are, in the order we're going to study them, the distribution of charge shaped like a very long cylinder. So imagine this, if I hold it vertically, this pencil, but imagine it continuing upward and downward so that it's a very long cylinder. That's a symmetric enough charge distribution that we can use Gauss's law to find the electric field. The next charge distribution is just a flat plane or sheet that goes off in 2 dimensions indefinitely, an infinite sheet of charge. We can use Gauss's law to find the electric field for that. And then the third distribution of charge is the most symmetric of all, a spherical distribution of charge. And then we can use Gauss's law to find the electric field for that. But if we follow the order in your book, the first charge distribution we're going to use is a cylindrical one. So let me remind you about Gauss's law, what it says in terms of an equation. It says that the electric flux through any closed mathematical surface must equal the total charge inside that surface over epsilon 0. That is true for any closed surface, absolutely any. But it's only really going to be helpful for us when we are looking for electric fields of one of these very symmetric charge distributions. So let's start with the cylindrical case. And what we're going to take as our kind of quintessential example of cylindrical symmetry is an infinitely long line of charge with a uniform linear charge density lambda, charge per unit length. So the SI unit for that lambda would be Coulomb per meter. Okay, that's what we have. The picture down there is representing such an infinitely long line of charge with a uniform charge per unit length lambda. It looks just like a very long line. And although they stopped drawing it, you are to assume that it goes on indefinitely upward and downward. And if you can see the little plus signs there, evenly spaced, they're assuming this linear charge density lambda in this case is a positive number, just to have something to think about. Our goal is to calculate the electric field E arrow at any location, absolutely anywhere. We have picked such a location, point P, in that figure. All right? Again, just to have something to think about. But we want to have a formula for the electric field anywhere. All right, well, the point P, you'll notice, is a distance little r from the center of the line, from the central axis of the line. And they happen to draw also a circle going through point P centered on the line for visual reference, and I'll talk about why we're doing that. All right, so here we go. Let's look a little bit farther down here on my screen. let's talk about the symmetry of the charge distribution and what that requires for the electric field that the charge distribution creates. Okay? Basically, because the charge distribution looks the same going up and down, right? You can't tell any difference between a point up here or down here or up there on this long line. The electric field vector can't have any property that depends on where you are this way, because the charge distribution doesn't care on where you are up and down. So the electric field can't have any property that depends on where you are up and down. So it can't have a component that points up or down, and it can't depend upon your vertical coordinate, whatever you label that, maybe, okay? So the electric field can only point, remember this line charge is positive, perpendicularly away from the line at any point, such as P. So let me try to draw it. So I have to go out there to the point P and just draw an arrow that points perpendicularly away from the line at that point. And that's got to be the direction of the electric field at the point P. Just points perpendicularly away from the line. We call that a radial direction. And so, if you want to be fancy, we say the electric field has what's called a radial component, meaning it only points radially away from the line. And the magnitude of that field can depend only on that radial distance you see there, little r, from the line. That's just based on the symmetry of that line of charge there. Now what that means is that if I were to pick a different point on this same dashed circle, how about over here? There's a new point over there. What can I say about the electric field vector there? Magnitude and direction. Well, the direction would have to point radially away from the line at this location, which would be roughly like that, yes? But its magnitude would be the same as the magnitude of the electric field over there on the point P. Why? Because the magnitude of the field depends only on the radial distance r from the line, and those two points I'm talking about are on that circle, and those 2 points are the same distance from the line. So those two electric field vectors that I've drawn with the purple arrows will have equal magnitudes, but different directions. Okay? All right, in fact, every point on that circle that we've drawn there is the same distance, little r, from the line, and at every point on that circle, the electric field has the same magnitude and points radially away from the line. Let's pick one more. How about the point over there on the circle? Can you sketch the electric field vector? Well, I didn't do a very good job there, I don't think. Radially away from the line at that point, roughly like that, but the same magnitude as the other E vectors, okay? All right, so we're going to use that knowledge of how the electric field must point and what its magnitude depends on to help us choose a Gaussian surface that's going to then help us get a very simple form for the electric flux through that Gaussian surface, okay? All right, so the next big step is key. Using our knowledge of the electric field vector to choose a Gaussian surface that we can apply Gauss's law to. How about we choose a Gaussian surface shaped like a cylinder that surrounds the line of charge? So we're going to choose a Gaussian surface, taking advantage of our knowledge of E. We're going to choose a cylindrical Gaussian surface of radius little r, right there, and height, some distance we'll call h. And then there we have it, right there. Do you see how it's shaded in that kind of a light orange color? I'll outline it just to make sure it's clear. The cylindrical surface, the Gaussian surface that we're going to pick is shaped like a cylinder that wraps around the actual line of charge. We have chosen that cylinder to have a radius r, which contains that point P I was showing you. and it has a height that's some amount h. That h can be anything we want. Okay? It turns out it's not going to matter what that h is. All right, so we're going to apply Gauss's law to that cylindrical Gaussian surface. Okay? That's what we're going to do. Now let's look at that surface a little bit and think about the electric field vectors we've got from that line of charge. Well, the cylindrical Gaussian surface, that's shaped like a kind of a soup can, is kind of naturally divided up into three parts. There's a circular top cap, a circular bottom cap, and then a curved side. And think about how the electric field's pointing radially away from this line at any given point, and think about where the electric field vectors will pierce this Gaussian surface, because that's where we get electric flux. And what I contend is, as I've written here, there are no electric field vectors piercing the top circular surface. They skim along it. Yes, they don't pierce through it. And there are no electric field vectors that pierce the bottom circular surface. They skim along it, but they don't pierce through it. Where I get piercing of the Gaussian surface from the electric field is on the curved side. And in fact, the picture here shows an example of that piercing with an electric field vector E piercing a little patch dA there on the curved side. So we get piercing of the electric field vector through the Gaussian surface on the curved side only. So now our task is to derive a symbolic expression, purely symbolic, for the electric flux in terms of the magnitude of the electric field and the dimensions of the Gaussian surface. Now again, the piercing occurs on the curved side, but notice something. Every point on the curved side of this Gaussian cylinder is distance r from the line, right? Remember that. The radius of the Gaussian cylinder is r, and every point on the curved side is a distance r from the line. And we said in the previous slide that the magnitude of the electric field, the magnitude of E arrow, depends only on that distance from the line. And every point on that curved side is the same distance from the line. So every electric field vector piercing the curved side has the same magnitude. And that's going to be very important. But let's start in our expression for the electric flux with, well, where we should start. The integral over the closed Gaussian surface of E dot dA. But because the Gaussian surface is shaped like a cylinder, it's quite natural to break that up into three parts. The integral of E dot dA over the circular top part of the cylinder, the integral of E dot dA over the circular bottom part of the cylinder, plus the integral of E dot dA over the circular, over the curved side. Three basic parts to that Gaussian surface just because it's shaped like a cylinder. Okay? Notice I did put a little circle on the integral symbol right there because the Gaussian surface is that closed cylinder. Circle means it's a closed surface. Notice I did not put a little circle on any of the other integral symbols you see there. Over the surface integral on the top part, or on the bottom part, or on the side part. Do you see why I didn't? It's not an oversight. Those three integral symbols there should not have the little closed circle symbol. My question is, do you see why they should not, those symbols? Do you see that if you look at those individually, the circular top part, the circular bottom part, and just the curved side, none of those surfaces are closed. That's why I didn't put a circular symbol on the integral symbol. Now here's what I can say about these three integrals. The integral of E dot dA over the top surface is 0. You see, we just said there aren't any electric field vectors piercing the top circular surface. They skim it, but they don't pierce it. By the same logic, the integral of E dot dA over the bottom circular surface is 0. There's no piercing of the bottom circular surface. All the piercing comes on the side, the curved side. Okay? So that's all that's left. Integral over the curved side of E dot dA. So now we're going to talk about that for a little bit. And to do that, let's just say a word about E dot dA, just that, E dot dA on the curved side. What can we say about E dot dA? Well, let's look at that little patch that we've got highlighted on the curved side. There's the E pointing perpendicularly away from the line, and the dA right there has to be perpendicular to the surface and point outward. So that would also point straight out like that. So when we do that dot product, we have magnitude of E, magnitude dA, and then I need the cosine of the angle between the E and the dA vectors. And there they are drawn right up there, and I hope you can see that they both point perpendicularly away from the line, so their direction is the same. So the angle between them is 0. Now the cosine of 0 is 1, so that's just going to be magnitude of E on the curved side, I'm just going to write it like that, times the magnitude of dA, which I'm just going to write like that. Okay? So over here then in my integral, I'm integrating over the curved side, magnitude E times magnitude dA. I have now collapsed that dot product into those two magnitudes multiplied together. Oh, but here comes another important step. And we have to be able to do this step or forget about using Gauss's law. It's not going to be helpful. At every point on the curved side, we said, the magnitude of the electric field is the same. So at every point on that curved side, the E is constant. What do we get to do in an integral with the part of the integrand that's constant? We get to bring it out front. So the next step is absolutely vital to having Gauss's law be useful. We bring the magnitude of E out front, and then we're just integrating over the curved side all the little areas of all the little patches that make up the curved side. But that integral now is very, very easy conceptually. When you add up all the little areas of all the little patches that make up the curved side, you just get the total surface area of the curved side. So what we now have, I'll write it right here, symbolically, for the total electric flux through that Gaussian surface is the magnitude of the electric field at every point on that curved side times the surface area of the curved side. Now we do have to remember a little bit of geometry. This is a cylinder. What's the surface area of the curved side? Well, you go around this way a distance 2 pi r, the circumference, and you go up and down this way a distance h. So you multiply those two distances, 2 pi r times h. Let me call that equation 1. Now that's just a symbolic expression for the electric flux in the case of cylindrical symmetry through a cylindrical Gaussian surface. We want to remember that. Magnitude E times 2 pi radius height. Going to be valid whenever we have cylindrical symmetry, our expression for the electric flux. And that's the left side of Gauss's law, as we know. Now there's more to Gauss's law than just the electric flux. There's also the enclosed charge. We need to derive a symbolic, a symbolic expression for the enclosed charge inside the Gaussian surface. And it's got to be in terms of the charge per unit length lambda of this line of charge because that's the quantity we're given. So let's go back up and look at our picture. Okay, there it is. The line is very, very long, and it's got a charge per unit length lambda, and we've surrounded it with a cylindrical Gaussian surface of radius r and height h. How much charge is inside that Gaussian cylinder? That's the key question. Let me declutter my picture a little bit. Okay. Do you see, first of all, you got to be able to visualize where the charge is that is inside the Gaussian surface. I'll try to draw it. It starts roughly right there, where the line intersects the top circular cap, and it ends down there, where the line intersects the bottom circular cap, and then all of the line that's in the interior there of the Gaussian cylinder is enclosed charge. So how much charge is that on that length of the line that I just shaded? We have to use lambda to answer it. Remember, lambda is the charge per unit length of the line. So you see how to get Q enclosed? Don't overthink it. The total charge inside the Gaussian surface is the charge per unit length of the line times the length this way, right? Which is h. That's another equation we're going to need, so I'll number that equation 2. And now all we do is combine our symbolic expressions for the electric flux, that's the equation I had labeled 1, and the enclosed charge, which is the equation I'd labeled 2, into Gauss's law, and solve for E. So here we go. Phi electric equals Q enclosed over epsilon 0. So we substitute equation 1 in for the flux, and we substitute equation 2 in for the enclosed charge. Remind you, there's the equation 1. E magnitude times 2 pi RH. Of course, you can see there equation 2 for Q enclosed. So E magnitude times 2 pi RH on the left equals Q enclosed lambda H, then divided by epsilon 0, and then solve for E. Of course, simplify, you can divide both sides by H, and then to solve for E, divide both sides by 2 pi R, and you get the magnitude of the electric field is lambda over 2 pi epsilon 0 R. And we get a pretty famous result for the electric field in cylindrical symmetry. You need to know two things. What's the charge per unit length of whatever line of charge is inside your Gaussian cylinder over the distance you are from the line? Notice it's r down there, not r squared. That's because an infinitely long line of charge is not a point particle. And we shouldn't expect to have an electric field that is this field for a point particle. Okay? So this is the result we use if we have a very long line of charge, because that has cylindrical symmetry. Okay? So here's a picture showing the line again and the Gaussian surface that we picked. And the property of the line is the lambda, linear charge density of it. And again, this picture shows the lambda as a positive quantity. And it shows one electric field vector out there on a Gaussian surface at a distance r. And we now know the formula for the magnitude of that electric field. E magnitude is the absolute value of lambda. That way we can even account for the case if lambda were negative, over 2 pi epsilon 0 r. Just watch out, that denominator is not 4 pi epsilon 0 r squared. Okay? This formula will get you the correct magnitude even if that line has negative lambda, negative linear charge density. Now we do have to account for the direction of the electric field. It's radially away from the line if the lambda is positive, just like this picture shows, right here. But what if the line that you had, the line of charge, draw it over here, had negative charge distributed uniformly along its length, so that the lambda we're talking about would be a negative number in coulombs per meter. Then you could still use the magnitude formula to get the magnitude of the field, but what would be the direction of the field out here at a point P? Well, the direction would be radially toward the line if the lambda is negative. So the arrow would point that way, radially, directly towards the line if it's negative. Okay? So now let's apply this to a situation where we actually have two cylinders and see how we can kind of get the most benefit, the most outcome of this result. So this is just practice. We're going to do it together. We're going to talk it through together. Okay? Gauss's law and cylindrical symmetry, but we're going to have two cylinders, or really a cylinder surrounded by a cylindrical shell. So here's the drawing, or the discussion. You can see the figure here. The figure shows a cylindrical metal shell that is coaxial with a thin wire. They have the same axis. Both are very long, so warning, the picture seems to imply that the metal shell just stops. Nah, that's just their way of, they have to stop, they just stop drawing it so you could kind of see things. But both things, the wire and the shell, go on and on and on, very long. Now that shell has an inner radius, Ri. I'll sketch it for a moment. Go from the central axis perpendicularly out till you get to the inner shell, the inner surface of the shell. That radius is Ri. And it has an outer radius Ro. So again, go from the axis, I'll go this way, until you get to the outer surface of the shell. That radius is Ro. That wire, which you can see is very thin, is right along the axis in the middle, and it has a uniform linear charge density plus lambda W. Plus, they're telling you that that wire is positively charged, and the charge per length they want to call lambda W, W for wire. The shell is electrically neutral. That means it has no net charge. No net charge. That's what electrically neutral means. Now, as we discussed in this section, the magnitude of the electric field produced by a uniform charge distribution with cylindrical symmetry, both of these things are that, is given by E equals lambda over 2 pi epsilon 0 r. And your author wants to refer to that formula as the cylindrical equation. And the purpose of this practice is to kind of show how we can get the most out of that result when we have cylinders. Okay? Okay, so here's the first question. Let's suppose we want to find the electric field value. Let me get that a little bit lower so you can see it a little bit better. At a certain radial distance. How about a distance r that's half of r initial? So now let me go up to the picture, let me declutter it, and let me try to, I'll just draw a circle surrounding the wire at roughly where we're talking about. That r. Half of r initial, halfway out in the hollow space to the inner surface of the shell. So we're in this area that you might call a gap between the hollow region, between the wire and where the metal shell begins. Notice metal, by the way, metal shell. That means conductor. Important. All right, if we're going to use the cylindrical equation to get the E there, we know its direction will be radially away from that wire because the wire is positively charged. And Gauss's law tells me that the only thing I have to worry about that determines the E on a Gaussian surface that would be where that would be shaped like a cylinder with a radius that's that red R there is the charge that's inside, the charge that's within that distance R. Well, the only charge that's within that radius R is the wire, right? We haven't got out to the shell yet. The only charge that's within the radius R is the wire. So the only charge per unit length value, the lambda value to use at the point we're talking about, is the lambda of the wire. Okay, that's the enclosed charge. So you use lambda W. And so you get E equals lambda W over 2 pi epsilon 0 R. And that's the formula you would use to find the electric field out there at any point, the field magnitude, at any point on that circle I've drawn there in red, which is a distance R from the center. Okay? Where the R we're talking about is 0.5 of R initial. That's how you answer part A. How about part B? To find E at a radius between R initial and or R inner, and R outer, what should we substitute for the lambda in the cylindrical equation? All right, now this one is, let's not overthink it, but it's a little bit subtle. Now let me draw a circle that's in between R inner and R outer. So something like that. That's now the R. It's between R inner and R outer. Now imagine a cylinder that goes at length h along there, along the axis, and has that radius. Couple things to note. Notice where the curved surface is. It's in that shell, isn't it? But the shell is metal. It's a conductor. What do we know about the electric field value if we're in the body of a conductor? It has to be 0. Here's another piece of physics we have to bring to this discussion. But that was an earlier section in this chapter. We must have E equals 0 inside the conductor. So our cylindrical equation has to give us 0 for E. The left side. But on the right side, the only thing that I have to deal with is the lambda and the R. Well, it's the lambda I got to talk about. Because what I got to think about now, based on Gauss's law, all that matters is what's the charge inside the Gaussian surface. So where is their charge inside the Gaussian surface? Now, look where the radius of it is, out inside that shell. Well, there's the charge from the wire, right, going right down the central axis. But that can't be all, because I got to have an E equals 0, so I've got to have a total lambda of 0. Right? So the two sides of the equation are the same. But I've got the lambda of the wire, which is positive. So there must be another lambda inside there that's exactly the negative of lambda wire. And where would that charge be located, that charge per unit length? It must be on the inner surface of the shell. Okay? So we use kind of lambda total, or lambda enclosed, equal to 0, so that we get an E equal to 0, where the lambda enclosed has two contributions. A positive contribution from the wire, the part of the wire that's inside the Gaussian surface, plus another part from charge that has now been induced on the inner surface of the shell. And that total must be 0. So in fact, okay, we're going to be able to learn what that lambda inner is. Okay? But in any event, the answer to B is that. That's the lambda you have to substitute in the cylindrical equation, because you have to get an E of 0 because your surface is in the body of a conductor. C. What is the linear charge density lambda inner along the inner wall of the shell, induced by the presence of that positively charged wire? And it's that equation I had right up there. Lambda wire plus lambda inner must equal 0. So the induced linear charge density on the inner surface of the wire, of the shell, must be just the negative of the lambda of the wire. And that's all you have to say for C. D. What is the linear charge density lambda outer along the outer wall of the shell. So now there's also going to be induced charge on that outer surface of the shell. Got to figure out how much that is. Well, remember, I know that the shell is electrically neutral. That means it has a net charge of 0. Shell is neutral. Any linear charge density that's induced on its inner wall, inner surface, when combined with any linear charge density induced on its outer surface, must equal 0. From which I can conclude that lambda outer is negative lambda inner. I'll use I for inner. But lambda inner is negative lambda wire. So this is just plus lambda wire. The same as the charge per unit length of the wire. Okay? Just like that. And then lastly, E. What if what we wanted to do was find the electric field at a radial distance of 2r outer? What should we substitute for lambda in the cylindrical equation? All right, let's draw a new circle. Now we're talking about a circle that's somewhere way out here. Outside. And now imagine a cylinder going down length h along the axis with radius r. And we want to find the electric field out on that, where I've got that red circle, or any part of the curved side of the cylinder. And I want to use the cylinder equation. Just figure out what to put in for the lambda. Well, it's got to be based on the total charge that's inside your Gaussian surface. So let's see where the lambdas are inside the Gaussian surface now. Again, imagine that it's shaped like a cylinder that goes down this way, distance h. Where's their linear charge density inside there? There's the wire, lambda w. There's the induced linear charge density on the inner surface, lambda inner, or I. And there's the induced charge density on the outer surface, lambda outer, lambda O. So the total lambda we have to include, lambda enclosed, is the lambda of the wire, plus the lambda induced on the inner surface of the shell, plus the lambda induced on the outer surface. And then use what we know about these various things. Lambda wire plus lambda inner, negative lambda wire, plus lambda outer, lambda wire. And those two cancel, and we just have lambda wire. That's what you would use if you're outside. So we've gotten the most out of that cylinder equation pretty much that we can. And we can then calculate the electric field when we have cylindrical symmetry, even if we have multiple cylinders, like we just saw. Well, I'm going to do one in class when we meet, and we're going to deal with what if the cylindrical distribution of charge isn't really thin like a wire, like is shown here, but it's big and thick. How will we deal with that? Still shaped like a cylinder. That's what we're going to talk about in our class, right? That's all for this video.